Good afternoon, everyone, and welcome back to this series of videos on the Solow growth model. Specifically, in this video, we're going to focus on another assumption that the Cobb-Douglas production function allows the Solow growth model to satisfy, which is constant returns to scale. So we know that, generally speaking, a function is like a machine that turns inputs into output. So we know there is this kind of relationship. So inputs go through this machine, which is our function, and become output. And constant returns to scale is fundamental in our case because it allows us to reroute the function in per worker terms, as we've already explored in more depth in a previous video. So let's begin by talking about functions in general. Specifically, when we talk about constant returns to scale, we talk about a function that is homogeneous of degree 1. So a function is called homogeneous of degree 1 if the following happens. So if when we write a function and we scale all of its inputs by a factor, let's say we have n inputs, and we scale all of them by a factor lambda, then what we're going to obtain is our original function scaled by the same factor lambda to the power of n, where n in our case equals to 1. Of course, we could have many different degrees of homogeneity. So we could have, for example, a degree of 2. So n could be equal to 2. In this case, it would mean that our output would more than double if we doubled all of our inputs, for example. So it really depends. But when we talk about homogeneous function of degree 1, we refer to the fact that, again, if we scale all inputs by the same factor lambda, then the output scales by exactly the same proportion. So everything grows in perfect proportion. So if you double every input, the output doubles, or if you multiply every input by 10%, then the output is going to rise by 10% as well. If you half all of the inputs, so if lambda was equal to a half, we would be halving final output as well. So there are many, of course, numbers that we can assign to this lambda, as long as it stays constant between the two sides of our equation. And what mathematicians call function homogeneous of degree 1, economists call constant returns to scale. So what does constant returns to scale actually mean? It means that if you increase your inputs by the same proportion, which is, again, lambda in our case, output will increase by that same proportion. And of course, we said increase, but we could also say, for example, decrease, and then the same would happen to output. The change would happen in always the same direction. So considering our Cobb-Douglas production function, at this point, you should be familiar with it, where we multiply capital to the power of alpha times labor to the power of 1 minus alpha. We can do an algebraic derivation of this. Specifically, why do we care about doing this algebraic derivation? Why do we care about this constant returns to scale property? Because think about a bakery, for example. A bakery produces cakes, and what we're basically saying with this constant returns to scale property is that if we double the number of ovens, which could be capital in our case, and we also double the number of workers that are dealing with the ovens, so we double the number of bakers as well, that we would be able to produce twice as many loaves of bread. So also you can think about it in terms of, for example, scaling and changing the, let's say, amount of ingredients that you put into a cake. So you can really think about it in real life terms and conclude that by saying that if the mix of inputs is the same, scaling the whole bundle up or down, of course, doesn't change productivity, which at this point is quite crucial to differentiate between productivity and amount of production. Because by productivity, we actually mean how much our inputs are able to produce in combination with one another, basically. Well, amount of production is just the total amount of output that we end up having. So what we need to show is that our Cobb-Douglas function here satisfies the fact that if its inputs are scaled by lambda, we are going to obtain lambda times the original amount of output that we had. So if this was our original amount of output, let's now scale every factor, so both k and l, by lambda. So we are going to obtain lambda k, everything to the power of alpha, and then lambda l, everything to the power of 1 minus alpha. And if we open the brackets and we distribute the power of alpha to each of the two terms that we have in each parenthesis, we are going to have lambda to the power of alpha, k to the power of alpha, times lambda to the power of 1 minus alpha, times L to the power of 1 minus alpha. So what can we do now? Since we have the same base here between lambda, the lambdas, and just a different exponent, we can combine them and we can sum up the two exponents so that we would have lambda to the power of alpha plus 1 minus alpha. And then timing this by k to the power of alpha, L to the power of 1 minus alpha, which are these last two terms. So look at what happens here. Alpha minus alpha is equal to 0. So we would end up having, so our production function with its inputs scaled by lambda would be lambda times k to the power of alpha, L1 minus alpha. And we said that this part here is our original output function. We can call it y to make our life easier. This is our original y, and we are multiplying it by the same factor that we used to scale each of the factor inputs. So yeah, basically, we've just proved that Cobb-Douglas kind of satisfies constant returns to scale, because this can be easily rewritten as lambda f, k, and l, which again is our original output function. And it's as if we've managed to take out the lambda from the inputs here, even if we scaled each of them separately. So Cobb-Douglas production function satisfies constant returns to scale. And since we've seen that it also satisfies positive and diminishing marginal product, it looks more and more as if this is an amazing shape for our production function in the Solow growth model. And in the following videos, we're also going to analyze how this can allow us to obtain some useful equations for pinning down graphs and specifically for analyzing comparative statics of our model. Thank you for listening, and I hope to see you all in the next video.